Welcome to this lecture in EE557. In the last lectures, Georgia taught you about the finite state Markov chains and how to control them. In this lecture, we are going to try to use the similar ideas for linear and nonlinear stochastic dynamical systems. But in that case, in the case of Markov chains, we had a finite number of state values, and in this case, we're going to have uncountably infinitely many state values to consider. So today's topic is going to be control of infinite state as opposed to the finite state Markov chains, whose state can take finitely many values. Infinite state stochastic dynamical systems. And we are going to consider both linear and nonlinear cases, but of course the examples that I'm going to solve will be linear systems because they are easier to solve on the board, but I would like you to consider also nonlinear systems, and in the second problem set I will actually give you questions about the nonlinear case. So we have the system equation xk plus 1 is equal to f of xk, uk, and wk. And I'm still considering the complete observation case, so we don't consider the partial information case yet. So we exactly measure the state vector, and uk is going to be given by a feedback policy which is Markov, given like this. All right? And here x0 is distributed with p of x0, and wk is distributed with p of wk, and we have our usual independence assumption, are all independent. Okay? So now we would like to apply optimal control to this stochastic system. And in that case, I need to, of course, define a cost function. So let us consider the finite horizon case. So I have k from 0 to n, and I would have ck, xk, uk given like this. So that is my cost function, and I would like to minimize this to find an input of this form. I need to find a feedback policy, or which is Markov, to minimize such a cost function. Of course, there can be many different choices for f. We can have different nonlinear systems, and ck is also arbitrary here. And we are going to apply the so-called dynamic programming to the control of such a system. In the case of a finite state Markov chain, remember we didn't have such an explicit equation for the state transitions. In this case, we have this type of expression with a process noise, and in the case of a Markov chain, we still assume that we measure the state exactly. We are going to be able to consider the partial information case when we don't measure the state exactly in the last 2 weeks of this semester. So here the first thing that we are going to do is to calculate this cost function. Given this feedback policy, given a specific feedback policy, how can I calculate this cost? Let us first concentrate on that. So calculating the cost function. So here the cost is given as this, Jg is equal to, I can take the summation outside, k from 0 to n, expected value of ck, xk, and uk here. Okay? And what I have to do here is to calculate such expected values. In order to be able to calculate such expected values, I need to consider what the probability distribution of xk is. Unconditional probability distribution of the state xk. If I know such distributions, then I can calculate these expected values. Expected value ck xk uk is equal to, we know that xk is stochastic here and it's distributed with this unconditional PDF, then this can be written as ck xk uk, and I would have p of xk dxk. Okay, this is the definition of the expected value. So this is the case when UK is deterministic. If UK is selected with this feedback rule, then I can of course replace this UK with GK XK as well. So I have CK XK UK. Instead of UK, of course, I'm writing here GK XK, so that this variable here, this function here, is only a function of XK now, and I have PXK dxk here. Okay? And as a result, in order to be able to calculate such an expected value, the only thing that I need to know is this unconditional PDF of xk. Remember, if this function f is linear, and if we have Gaussian noises here, and with a Gaussian initial condition, then I can calculate all of these marginal, unconditional PDFs of the states as Gaussian distributions with some mean and covariance. And then I can take this expectation. So even when we don't have Gaussianity and when we don't have linearity here, we can calculate the marginal distribution, marginal unconditional distribution of the state, and we can substitute it into this formula. But here this is really quite general. So without actually knowing the specific system and knowing the specific distributions of the process noise and the initial conditions, I will not be able to know this P of xk. Okay? So as a result, I will actually leave this calculation here like this, and I will go into the second way of calculating this cost here. And that is going to be the recursive calculation of the cost, which is also going to be useful for control purposes for dynamical programming. Okay? So here actually we have also another type of theory to calculate this P of xk recursively, just as we did in the case of finite state Markov chains. So for example, I can actually give you a brief idea about that. If I would like to calculate this, so I have the following equations. I have x0 distributed as P of x0, and I would like to know what the distribution of x1 is. Okay? And in that case, in the coming lectures, we are going to be able to write this like this. P of x1 is going to be actually P of x1 given x0 times P of x0 dx0. Okay? This formula is the continuous equivalent of the formula P1 in the case of a Markov chain. P1 is equal to P0 times the transition probability matrix. Okay? So instead of this, I can write P0 times capital P, which is a transition probability matrix. In this case, in the earlier case, we had a vector vector with finite number of elements for the state distribution. In this case, for this distribution, we have infinitely many values for this density. Okay, so we see that here the obtaining P of x1 is nothing but in the case of finite state Markov chain, is multiplying the transition probability matrix with the earlier distribution. And here, I have, of course, vector matrix multiplications and summations, okay? So in the case of continuous state, this is the earlier distribution. So this behaves like P0, and this thing behaves like the transition probability matrix, which is the one-step transition PDF here, okay? And this is my P1. So if you think about this P of x1 as a horizontal vector with infinitely many elements, then this integral is nothing but this vector and matrix multiplication. This is my earlier distribution vector, and this is my transition probability matrix. And the integral just represents the vector matrix multiplication here, okay? And that gives you this. So here, what would I do? In the case of calculating P of x2, then I need to use P of x2 given x1, P of x1, d of x1. Okay? So I apply this procedure once more. So in the case of a finite state Markov chain, we had another P multiplication here. So in the case of a Markov chain, P2 is equal to P1 times P, but P1 is P0 times P. So this is P0. P squared. In the case of a continuous state, things are not really that easy like this matrix multiplication. In that case, of course, instead of this P of x1, you can substitute this integral here, and then you can try to calculate P of x2 using double integrals. Okay, but there is an easier way, and it is to use two-step transition PDF. So P of x2 is at the same time integral Px2 given x0, P of x0, d of x0. Okay, this is also correct. And in this case, instead of this P square, which is a two-step transition distribution in the case of a finite state Markov chain, I need to use in the integral two-step transition PDF. Okay? So as a result, our way of calculating this cost, this is the first way of calculating this cost, is to write this P of xk. P of xk is integral P of xk given x0. This is the k-step transition distribution. And I would have P of x0 dx0. Okay? If I substitute this into that integral, then I would get the following result. Integral ck xk gk xk, and I would have this integral then comes P of xk x0, P of x0 dx0, and then I have my integral with respect to dxk. Okay? So this expectation is therefore nothing but the following. So I would have here. So I would actually write the same thing, but in a neater way. Ck xk gk xk here. And I have the other integral, Pxk given x0, P of x0 dx0 dxk. Okay? In the case of the finite state Markov chains, remember we had the following formula. This was pi 0, the initial state distribution, which is given by this in our infinite state system. And I would have pi to the k-step transition probability matrix, which is represented by k-step transition PDF in our infinite state system. And I would have CG here, which is represented by by this term. So in the finite state case, we could write things quite easily using vector matrix multiplications, but here these two multiplications in the case of finite state Markov chains would turn into these two integrals here. Okay? So this is the first way of calculating the cost, and we can of course do this and we can solve examples on this, but this is not going to be useful for us in the case of control. So we are going to directly go into the second way of calculating the cost, which is the recursive way. And we are going to see that the recursive way is much easier to apply, and it is also going to be useful for us in applying optimal control ideas to these infinite state stochastic dynamical systems. Okay? So now let us look at the recursive calculation of the cost function. Of the cost function. So here we are going to again define the so-called cost to go function. Okay, so this cost to go function, so I would have cost to go function, it's going to be shown as Vk of xk, and it is defined as follows: expected value of the cost from time k to the final time CL, XL, UL, given that the state at time k is xk. Okay? This is our cost to go. So we are looking at the time k and afterwards. We are summing the cost from time k and to time kn, and we are setting our state at the state xk at time k. Okay? So then we know that we could calculate these functions recursively, and that is going to be the fundamental idea in actually dynamic programming, and we are going to be minimizing these functions, these cost to go functions in dynamic programming recursively. So of course here we are going to come up with a recursion. Let us look at the initialization of this recursion. We are going to start with Vn of xn, and this is going to be by definition, instead of k I will substitute n. L equals to n, from n to n, CL, XL, UL, given xn. Okay? And you see that in this summation there is only a single term. So I would say here, this is going to be the expectation of a single term, and L is equal to n, and it is xn, un, given xn. So here, in this case, when xn is given, then this term is just deterministic for this expected value, and furthermore un is given by our feedback policy, Markov policy. Is also deterministic. So that means that there is no need for this expected value, and this deterministic quantity can get outside directly. So I have this is equal to Cn xn un. Okay? So that is the initialization of our recursion. Remember, our recursion is backwards, and this is the final time. We are starting these functions from the final time by equating the final cost to go function to the incremental cost itself. Okay? So this is our initialization. Now let us try to come up with a backwards recursion for this cost to go function. For that, I need to define what Vk plus 1 xk is. So vk plus 1, xk plus 1. So this is the cost to go function at time k plus 1 is given by this definition by replacing these k's with k plus 1. Okay? So this is expected value L from k plus 1 to n CL XL UL given xk plus 1 now. Okay? And in order to be able to come up with a recursive formula, maybe I should erase this one as well. The recursive formula, I will try to express Vk of xk in terms of Vk plus 1, xk plus 1. We set the final value and then we are going to be coming backwards. That after calculating this Vn, I'm going to be calculating Vn minus 1 and n minus 2, etc. So given Vk plus 1, I will try to go to Vk. So now let us try to write this Vk in terms of Vk plus 1. Okay? So this is by definition expected value of this sum here. I will separate the first term of this summation. The first term of the summation is ck, xk, uk, and I have the rest. L from k plus 1 to n. Why did I separate the first term? Because I see that in Vk plus 1, the summation starts from k plus 1. If I want to express this in terms of this, then I need to separate this the first term from that summation. So I have CL, XL, UL here, given xk. Okay? So now if I look at this first term, xk is given to us and uk is also given to us by this feedback policy deterministically when xk is given. And as a result, this ck term can get outside the expectation directly. ck, xk, uk plus expectation for the rest. L equals to k plus 1 and CL, XL, UL given xk. So do you think this is equal to Vk plus 1? If you compare these two, you see that the only difference between these two expectations is that their given conditions are different. Okay? Here I have the given condition xk, here I have the given condition xk plus 1. In order to overcome this difference here, I will use the law of iterated expectations. Remember, law of iterated expectations tells us that x given expected value for any two random variables, expected value x given y is equal to expected value, and I have an inner expected value, x given y and z here, and I would have y here. For any random variable z, I can actually write such an iterated, law of iterated expected values for this. And here, in order to be able to remove this difference, xk plus 1 from here, and to get xk plus 1 in the given condition, I will add an additional expectation into this expectation. Okay? So I would have C of xk, gk, sorry, I have uk still here. I have uk plus expected value. I would have another expected value here. And whatever is inside there, I would put that here as well. L from k plus 1 to n, CL, XL, UL. And I would have, in the given condition, I need to keep this xk because y is in both of the conditions here, and I can add any variable I like into the inner expectation. So I have here xk, and now I just add xk plus 1. Okay, I choose my z as xk plus 1, and this is my xk. So now is the time to use the Markov property. I know that here in this summation, x's are starting from xk plus 1. Okay? And here in the given conditions, I have xk plus 1 and xk. Because of the Markov property here, I can remove this previous state from the inner expectation, because the states in these summations are xk plus 1, xk plus 2, xk plus 3, etc. So given xk plus 1, I can remove this xk due to the Markov property of the system. Okay? So remove thanks to Markov property. Okay? And that is going to be equal to, of course, if there were previous states here, I wouldn't be able to do that. Okay? If I had, for example, xk minus 1 here in this summation, I cannot remove this thing. So the Markov property holds because the states here are xk plus 1, xk plus 2, etc. All right? So there is here the use of the Markovian property of that system. And I have C of, sorry, here there is ck, I think, ck, xk, uk, plus expected value. I have the inner expectation now. L equals to k plus 1 to n, cl, xl, ul. In the given condition, I have only xk plus 1. And I have given condition of xk in the other expectation, outer expectation. So now I see that here, this inner expectation is nothing but my vk plus 1, xk plus 1. Okay? So I can actually write here my recursive formula. This is equal to ck, xk, uk plus expectation. The inner expectation is nothing but vk plus 1, xk plus 1 given xk. So far here, we have nothing different than the finite state Markov chains. Okay? But from this point on, we are going to be able to make some simplifications. So here, let me try to write this ck, xk, uk. I can actually write this expectation in the following way. vk plus 1, xk plus 1, pxk plus 1 given xk, dxk plus 1. Okay? It is this expectation in integral form. Okay? I put here the conditional distribution of xk because in this expectation there is this conditioning xk, and the expectation is with respect to xk plus 1. Okay? So now if you look at this formula, remember this is vk of xk. In the case of finite state Markov chains, we have obtained the following formula. Vk is equal to ckg plus I would have here this transition matrix, and I would have vk plus 1. Okay? And here actually I can add uk as well. Okay? So this was the formula in the case of finite state Markov chains. And now try to compare this. Vk is this one. So, and I have ck is given like this. If I substitute uk is equal to gkxk, then I would obtain this term. And here, this expectation is nothing but, in the case of finite state Markov chain, this integral turns into a summation and multiplications here. So this is the transition probability matrix, which is represented by this in infinite state case. And I have this vk plus 1 here, and integral is represented by the matrix vector multiplication there. Okay? So this is the equivalent formula in the case of infinite state systems. All right? But we are not going to use this because we are going to get an even simpler formula here. Okay? Now, instead of continuing in this way, I would instead continue from this point to get an easier result. So this is equal to ck xk uk plus, instead of xk plus 1, remember in the case of finite state Markov chain, I cannot express xk plus 1 as a function, as an explicit function of xk, uk, and wk. There is an implicit transitions, etc., but there is no such formula in the case of finite state Markov chains. So after this point, in the case of finite state Markov chains, I need to use this, okay? There is no other choice. But here I have a choice, and that choice is to replace xk plus 1 with its formula here, coming from the dynamical system. Okay? So that is equal to expected value vk plus 1. Instead of xk plus 1, I write f of xk uk wk given xk. Okay? So now things get really simple, because xk is given to us. As a result, this term is deterministic. uk is given to us in the Markov feedback policy. So uk is also given to us, given xk. So these two terms are here deterministic. Okay? So the only thing that we need to take this expected value with respect to is this process noise wk. Okay? The only stochastic term here in this expectation is wk, because xk is given to us, which means that xk and uk are known. Okay? So that means that I can replace this expectation with an expectation with respect to wk only, which is going to give us our final formula, vk, ck, uk. So this is vk, xk. And that is equal to plus expected value vk plus 1 f of, in this case, this expectation has to be taken only with respect to wk. I will show this as a subscript in the expectation sign. Okay? xk, uk, and wk. So here I remove the given condition because I write here an expectation with respect to only wk, which means that all the other variables should be considered deterministic. Okay? So then what is this expected value? It is nothing but this quantity times the process noise distribution and the integral. Okay? So this is equal to, so this is our final formula, but if I would like to write this expectation in the integral form, what I can do is this. Vk xk is equal to ck xk uk plus, instead of this vk plus 1, I can write expected value, I can write an integral vk plus 1 f of xk uk wk times the process noise distribution, dwk. This is my expectation with respect to wk. Okay? And of course, instead of uk here, I can write gk of xk. All right? So this is my recursive formula. From vk plus 1, we get vk. In this manner, we go backwards. And then, by going backwards, we can reach V0. Okay? So this is our backwards recursion. Backward recursion. Okay? And we know that we are going to run this for k equals to n. For k equals to n minus 1, and I will go with steps of minus 1 here, and I will continue until k equals to 0. All right? And here we can calculate what V0 x0 is. by the definition of Vk, V0 x0 is nothing but expected value k equals to 0 to n c, sorry, let me put L here, CL XL UL given x0. This is a definition of V0 x0, and we know that we can calculate this thing by going recursively backwards. Okay? And now I need to calculate from this V0 x0 what the final cost is. Remember, our cost is expected value k from 0 to n, ck, xk, uk, and that's all. So the only thing that I need to get rid of here to calculate j from V0 x0 is to get rid of this given condition. So you see that the only thing different between these two quantities is this given condition. So if I can get rid of this given condition, the result is going to be j. So then j is going to be, how can I get rid of this given condition from this expectation? If I take expectation once more of this quantity, then it is going to be, by the law of iterated expectations, it's going to be the expectation of this quantity only, without any given conditions. That means that our Jg is going to be expected value of V0 x0. Okay? And what is this expectation with respect to? It is with respect to just x0. Okay? And what is this expectation? It is integral V0 x0 p of x0 dx0. This is the integral form of the expectation operation. And this is the final cost calculation. So we will start with Vn. We know what we need to set Vn to. And then we go backwards. We calculate V0. And then we take the expected value of V0 with respect to x0 to calculate the final cost. This is the recursive calculation procedure for the cost. So now we are actually ready for an example. In the example, as I told you, I would have a linear and Gaussian system, but you need to practice yourself with possibly nonlinear systems and possibly non-Gaussian systems. Example. So I have xk plus 1 is equal to xk plus uk plus wk, and I have complete information case yk equals to xk, and I am given the feedback policy like this, g of xk. I have a stationary Markov policy, and that is given as -1/2 times xk. Okay? And x0 is given as normal with mean 1 and variance 1. Wk is given as normal, wk, mean 0 and variance 1. And we know that x0, w0, w1 are all independent. Remember, this is necessary for the Markov property to hold. And I have here the cost that I would like to calculate is this one. Expected value k from 0 to 1, xk squared plus uk squared plus 2x2 squared. Okay? And I will calculate this cost recursively. So here, of course, this type of formulation is not strange for us. Here we see that n is equal to 2 here, okay? n is equal to 2, that is our horizon variable, and I would have C2 of x2 U2 is equal to 2, it is just this, C2 of x2. So the last cost function is independent of U2, and it is only a function of x2, and this is 2x2 squared. Okay? And C1 of x1 U1 is equal to here x1 squared plus U1 squared, and C0 x1 U1, sorry, C0 x0 U0 is x0 squared plus U0 squared. Okay? So we see that here, if I would like to optimize here with respect to the input, then there are only two inputs, U0 and U1, to optimize with respect to. But here we are not optimizing, we are only using this feedback policy to calculate this cost, to calculate this cost here. We need to know what this cost is for this given policy. So now let us start our procedure. Let us start our initiation with V2 of x2. V2 of x2 is going to be just this function here, which is C2x2, and it is 2x2 squared. 2x2 squared. So there is nothing to do more here. Then I will go into V1 of x1. Okay? V1 of x1 is going to be, of course, C1 of x1 U1, and I would have plus expected value V2 of into V2. I will write my f function. So this is going to be f of x0. Sorry. This is going to be f of x1 U1 and W1. Okay, and this expectation is going to be taken with respect to W1. Okay, so now I know what F2 is, sorry, I know what V2 is, and I know what F is. F is this linear function. Okay, so now let us try to write this. C1 x1 U1 is this, x1 squared plus U1 squared, plus expected value with respect to W1. I have V2 of x2 is 2x2 squared, and instead of x2, I would write just this f of x1 U1 W1, and it is just this one. So I have here 2x2 squared, 2x1 plus U1 plus W1 squared. Okay? So this is my V1 of x1. So now let us use the feedback policy. I know that U1 is minus 1 over 2 x1. So I will substitute it into these formulas. So I have that is equal to x1 squared plus U1 squared is given by this 1 over 4 x1 squared plus expected value. I can actually take 2 outside because expectation is linear. So I can write here 2 expected value times x1 plus u1. I have x1 here, and u1 is minus 1 over 2 x1, which would give me 1 over 2 x1 plus w1 squared. Okay? And this expectation is only with respect to W1. Okay? So I am assuming the other variables are deterministic here. That is equal to, I would have here 5 over 4 x1 squared plus in 2 parentheses, I would have 1 over 4 x1 squared. x1 is deterministic and it can get outside the expectation directly. And I would have plus, these two are going to be multiplied, and I would have expected value W1. Let me write, I will write this in the long way so that it's clearer. Okay? So I can do these calculations automatically, but I will write it in a long way first, and then it is better it's easier to understand. So I have 5 over 4 x1 squared plus in two parentheses expected value with respect to W1, it is 1 over 4 x1 squared plus x1 W1 plus W1 squared. Okay? So now I'm taking expectations with respect to W1. All right? So I have 5 over 4 x1 squared plus this thing is with respect is only related to x1, and x1 is deterministic here. I can take it outside expectation directly. So it is going to give me 1 over 2 x1 squared plus this term. It is only W1 which is stochastic here, x1. So I would take it. So I would write this as x1 can get outside the expectation, x1 times expected value of W1. And of course, this thing is going to be 2 expected value W1 squared. Now, W1 is distributed according to this Gaussian distribution. Its mean is 0, which means that this term is 0 here. Okay? And its variance is 1. And this is nothing but the variance of W1. So this term is 1. Okay? And I would write this as, if I sum these two terms, it is 7 over 4 x1 squared plus this term is completely 0. And this term is going to give me just 2. Okay? So which means that I have V1 of x1 is 7 over 4 x1 squared plus 2. Okay? Let me check my notes. Yes, it is correct. So now we are going to continue this logic towards calculating V0. All right? We have calculated V1. Now let us calculate V0. V0 of x0 is equal to, I have here first C0, x0, U0, which is this thing, x0 squared plus U0 squared plus expected value with respect to W0. I am going to use this V1 formula here, and instead of x1 there, I would substitute x0 plus U0 plus W0. Okay? So I will write this into the expectation, 7 over 4, and instead of x1, I'm writing x0 plus U0 plus W0 square, which is there, plus 2. Okay? So now let us use our U0 formulas here. U0 is given by minus 1 over 2 x0. That is going to mean x0 squared plus 1 over 4 x0 squared plus x. So let me distribute this expectation with respect to this summation inside. So I have 7 over 4 expected value of W0 of this quantity, and U0 is minus 1 over 2 x0. So that means that this is 1 over 2 x0 plus W0 square. And if I consider this term, this is just a constant inside the expectation. It's going outside directly. So I have plus 2. Okay? So now let us continue. I have 5 over 4 x0 squared plus 7 over 4 parentheses here. I would have 1 over 4 x0 squared, which is going directly outside the expectation. And then I have expected value with respect to W0 of multiplication of these two times 2. Okay? But we know that it's going to necessitate taking the expected value of W0, which is exactly equal to 0. So there is no cross term here. And I would have the last term here plus expected value of W0 square, which is 1. Okay, and I would have plus 2 here. All right. So now I have taken the expectation directly. So now let me look at these terms. 5 over 4 x0 squared plus 7 over 16 x0 squared plus 7 over 4 plus 2. All right? So now if I combine these terms, equate the denominators, so this is going to be 20 over 16, so it is 27 over 16 x0 squared plus summation of these two would give me 15 over 4. All right. So now we have calculated V0 of x0. V0 of x0 is 27 over 16 x0 squared plus 15 over 4. So now I'm ready to calculate the cost, the final cost here. And for that I'm going to take the expected value of V0 x0. Then the cost for this feedback policy is J is equal to expected value of V0 x0, and which is that function here. Expected value 27 over 16 x0 squared plus 15 over 4. And this is going to give me 27 over 16 expected value of x0 squared plus 15 over 4. And what is the expected value of square of x0? Is this the variance of x0? Expected value of x0 square. If x0 has 0 mean, then that would be the variance. But if x0 has non-zero mean, that would not be the variance. So remember, covariance of a vector is given as expected value x transpose minus expected value x transpose. There is such a formula, and in the scalar case, this would be variance of x is equal to expected value x squared minus expected value x squared. Okay? And we see that this gives us the formula expected value x squared is equal to variance x plus expected value x squared. Okay? So we see that if the random variable has 0 mean, then the variance is equal to expected value of x squared. W was 0 mean, so expected value of w squared would be its variance. Okay? But x0 is not 0 mean. Okay? This is the distribution of x0. And we see that its mean is 1 and its variance is 1. So as a result, this quantity here would be the summation of the variance of x0 plus its mean square. Okay? So that is equal to 27 over 16, and I would sum the variance and the expected value square here. Okay? That is going to be 2 times 2 plus 15 over 4. Okay? This is 27 over 8 plus 15 over 4 here. All right? And this would be here. Equate the denominators here. So it is 57 over 16. And if you calculate this, then it is 7.125. This is the cost of applying the feedback policy. U is equal to minus 1 over 2x. Okay? So remember, I solved this example which involved a linear system and a quadratic cost function you need to try yourself as an exercise, try to consider nonlinear systems and also non-quadratic cost functions. And you would try to understand what you would need to do in those cases, how to calculate this type of expectations and how to apply this procedure. So that completes our investigation of calculation of the cost function. And now we can go into the dynamic programming for this type of systems. So let me write dynamic programming. For infinite state stochastic dynamical systems. In this case, we are going to do exactly the same of what we did for finite state Markov chains, okay? And in order to be able to find the optimal feedback policy, optimal Markov feedback policy, we are going to try to minimize these cost to goes at each step, okay? So let me try to write the idea here. So we would like to calculate the optimal cost by minimizing our cost function, expected value k from 0 to n, ck, xk, uk, and with respect to what? The minimization is with respect to these variables. uk is equal to gk, xk, and I would minimize this with respect to k from 0, 1, up to n, okay? And in order to be able to achieve this multidimensional minimization, we are going to use our concept of cost to go. So we are going to divide our multidimensional optimization problem into individual single-dimensional optimizations by minimizing these cost to goes at each step. And again, we are going to go in backwards direction, and at each step, we are going to minimize cost to go with respect to only a single input, okay? And then after doing that optimization, we are going to go one step back, and we are going to do the optimization with respect to the new or the previous input variables, and that is going to give us at the end the optimal strategy or the optimal feedback policy, which is usually non-stationary. So at each time step, we're going to get a different input feedback rule. So here, in order to be able to achieve this, I define my optimal cost to go, which is Vk star of xk is the minimization of this cost to go expected value of L from k to n. I have CL, XL, UL, given xk here, and here in this cost to go here, I have the input terms UK plus 1, UK plus 2, etc. I will define this function as the minimization of this cost to go with respect to all of these input variables from UK to UN. Okay? This is my optimal cost to go function. And this is the optimal cost that you would obtain in time if you start your optimization at time k, and if you set the state at xk, this is the optimization of the future input values. Okay? If I know this function, then I can try to go backwards here. Okay? in order to be able to obtain Vk minus 1, etc. So here is what I'm going to do. I will try to write a recursive formula for these optimal cost to go functions. Suppose that I know this Vk plus 1 star. Vk plus 1 star of xk plus 1 is the optimal cost to go for time k plus 1. Okay? This is going to be the minimization of uk plus 1 to n, and I would have expected value of, I would have L from k plus 1 to n, and I have CL, XL, UL, given xk plus 1. So when xk plus 1 is given to me, this cost to go at, so this is Vk star, and I have at time k plus 1, I have xk plus 1, and I have Vk plus 1 star here. This is the optimal that I can do at time k plus 1. Okay? So I have a state here, state xk. If the state is one-dimensional, the state xk is on this line. And I have the state at xk plus 1. Okay? And suppose that I know Vk plus 1 star, and suppose that I need to calculate what Vk star is at time k. Okay? So let me try to write this optimal cost to go at time k in terms of the optimal cost to go at time k plus 1. Okay? So I have Vk star at time k is equal to, now compare the expectations here. So this quantity in the expectation starts from k plus 1, and this quantity in the expectation starts from L equals to k. Okay? So here I will just write this. So first I need to add this extra term here in this summation. So I would get ck, xk, uk here. Okay? Between these two summations, there is only two terms different. Sorry, there is only one term different. And that term is ck, xk, uk. Okay? And we see that in this Vk star, optimization has been done with respect to uk to n. And in this Vk plus 1, optimization has been done for uk plus 1 to un. Okay? So here, in this minimization, the only missing variable is uk. So here uk, optimization with respect to uk is extra. Okay? So I separate this extra term in the summation and I write it here. This is the cost of being at state xk and selecting the input uk. Okay? And from this point on, I will go to the state xk plus 1. Okay? I add this term, and when I go to state xk plus 1, then I need to optimize with respect to those inputs as well. uk plus 1 to un. But this optimization has already been done, and it is given by this Vk plus 1 star. So I'm adding this here, Vk plus 1 star xk plus 1. Okay? But here, the thing is that we don't know what xk plus 1 is. Okay? So when I start with it, for writing Vk xk, I know what xk is. Okay? But I don't know which xk plus 1 I'm going to go here. Xk plus 1 is a stochastic random variable. As a result, I'm going to put here an expectation, and I will write the given condition xk. Okay? So this is the formula for these Vk stars. There is here only one thing missing. In this vk plus 1 star, the optimization has been done with respect to uk plus 1 to n. Okay? Optimization has been done in vk plus 1 xn for uk plus 1 to until un. Okay? So here, when I try to write vk star, we see that there is a uk dependence here, and in xk plus 1 there is also uk dependence. Okay? So in order to be able to complete this story, the only thing that I have to add here is vk plus 1 star xk, sorry, vk xk is equal to minimum with respect to uk of this quantity. Okay? So I am adding the extra term here in this summation like this, and then I am adding the optimal cost that I would obtain if I'm at state xk plus 1, but xk plus 1 is stochastic. As a result, I add an expectation here, given xk, and I finally minimize the result with respect to this additional input that comes from passing from vk plus 1 to uk. uk is extra here compared to this minimization. Okay? So now the only thing, so this is actually the formula also that we used in the case of finite state Markov chains. What is going to be different here is that I will replace this xk plus 1 again with this formula given here. Okay? And I will replace this expectation into an expectation with respect to only the process noise. Okay? So here let us do that. Vk star of xk is equal to minimize with respect to uk, and I would have ck xk uk plus expected value with respect to the process noise wk, and I would have here vk plus 1 star. Instead of xk plus 1, I would write f of xk uk wk, and that's all. Okay? And what is the optimal input? Then uk star is equal to the argument of this minimization. Arg mean uk ck xk uk plus, sorry, I need to repeat this, xk uk wk, and that completes. And so this is going to be usually a function. This is gk star of xk. So we see that here xk acts as a deterministic variable here. So when I make this minimization, the minimum of uk is going to be with respect to xk. For each xk there would be a different minimum as a function. So that means that this uk star is going to turn out as a function of xk at the end of this minimization. Okay? So now let us try to write our general algorithm for the dynamic programming. Here, as you see, in the case of finite state Markov chains, we use the infimum concept. I really do not like to use it here. Instead, I use the minimization. So I assume that this minimum always exists, and the function takes that minimum value at some point u star. Okay? So here, what is our initialization for dynamic programming? Initialization is done as before. Vn star of, before that, let me write the cost function. So the cost function that we consider is always going to be in this form. K equals to 0 to n minus 1 ck xk uk plus cn xn. Okay? So there is no input term in the last term here. This is because the input un affects only the future states, xn plus 1, xn plus 2, which are outside our horizon. Okay? So we don't consider the input un in the last time step. So if this is our cost function, then we start our initialization for the dynamic programming as follows. We set v star of n, xn, as cn of xn. There is nothing to optimize here. Okay, in the last step, there is nothing to optimize, so just we start our recursion with this optimal cost to go, which is the earlier formula that we used. And then we have the backwards recursion. It is those formulas. Vk star xk is equal to, repetition it might be boring, but it is usually good for understanding the difficult concepts. So I have ck xk uk plus expected value with respect to wk, and I have vk plus 1 star f of xk uk wk. Okay, and the input is set as the argument of this minimization. Okay, so uk star is the argument of this minimization. Okay, and what about the final cost calculation? It's the same as before. So the final cost calculation, so we do this, we apply this recursion from time n minus 1 up to time 0. So then j star happens to be expected value of v0 x0. Okay. So now we are ready to apply this dynamic programming concept to this linear system that we have seen in the earlier example. I will unfortunately have to write this again. Xk plus uk plus wk. Yk is equal to xk. uk is equal to gk xk. And x0 is normal x011. Wk is normal wk01. And x0, w0, w1, they are independent. Okay? And in this case, I need to find the optimal cost, j star. I need to minimize the earlier cost that we have used. K from 0 to 1, xk square plus uk square plus 2x2 square. And I need to do this minimization for uk is equal to gk xk for k is equal to 0 and 1. All right? So now I need to find the optimal inputs, and I need to find the optimal cost here. And for that, I need to use the concept of dynamic programming. Let us start our recursion with v2 star of x2 is equal to 2x2 square. It is just this thing. So now I'm ready to calculate v1 star. v1 star of x1 is equal to, I need to do the minimization with respect to u1, okay? And I need to first add the incremental cost, x1 square plus u1 square, plus I need to use an expectation of v2 star. I have V2 star given like this, 2x2 star, but x2 is x1 plus u1 plus w1. And this expectation is with respect to w1, okay? 2x1 plus u1 plus w1 squared, all right? So the first task that I'm going to do is actually to calculate this expectation. So I have minimize u1. Sometimes actually doing the minimization before expectation might be more useful. But here I would like to calculate the expectation first, and then I will minimize with respect to u1. So I have here x1 square plus u1 square plus I will expand this summation into these two terms, x1 plus u1. These are my deterministic terms because x1 is given to us, and these are going to be w1 is the stochastic term here. So let us write this: 2 expected value w1 x1 plus u1 square plus 2 x1 plus u1 w1 plus I have also w1 square, okay? So I have minimize with respect to u1 x1 square plus u1 square plus this term is deterministic, it gets outside the expectation directly because it doesn't depend on w1. And this term, when I take expectation, these terms would get outside. Let me write it. 2, so that would be 4 x1 plus u1 times expected value of w1 plus 2 expected value of w1 square. So we know that expected value of w1 is 0. So this cancels, and expected value of w1 square, because w1 has 0 mean, this is the variance of w1, okay, which is 1. All right? So the cost function that I need to optimize turns out to be this: u1 x1 square plus u1 square plus 2x1 plus u1 square. And this term cancels out because of this expectation property, and I would have 2. All right? So now I would have to do this minimization with respect to u1. So sometimes some constraints for u1 can also be given. So u1 might be, for example, between -1 and +1, and then you need to apply this minimization with some constraints. That is also possible. But here we don't have any constraints, so I can just equate the derivative of u1, the derivative of this cost function with respect to u1 to 0 and solve for u1. If a constraint is given, then you have to consider also whether the optimization results ends at boundaries or not. Okay? So here, let me take the derivative with respect to u1. It is 2u1 plus 4, and I would have here x1 plus u1 is equal to 0. Okay? So now I can cancel this 2. There is a 2 here. So I have u1 plus 2x1 plus 2u1 is equal to 0. So I have 3u1 is equal to minus 2x1, and u1 is equal to minus 2 over 3x1. I will just put a star onto this u1. Okay? So this is my G1 star of x1. Okay? So this is the optimal input at time 1. This is the optimal feedback strategy at time 1. And we see that it turns out to be a linear feedback rule. So I would have to feed the state back by multiplying it with the gain minus 2 over 3. And this is my G1 star of x1, my optimal control at time 1. So when the system runs, x1 is stochastic, okay? But we measure here x1 because the output is exactly equal to x1 here, we first see what x1 is, and then we apply this input. We multiply it with -2/3, and then that input, with that input, system transitions to x2. Okay? So then I will substitute this input value here into the cost function to obtain v1 star of x1. v1 star of x1, then I will just substitute this u1 star instead of u1. So I would have x1 square plus 4/9 x1 square, this is u1 square, plus 2 times, substitute this u1 there, so it's going to give you 1/3 x1, so it is 1/9 x1 square plus 2. Now if I calculate this v1 star of x1, then it's going to be 9 plus 4, 13, plus 2, I have 15/9 x1 square plus 2, and 15/9 is 5/3 x1 square plus 2. Okay? This is our optimal cost to go at time 1. So we have found the feedback strategy, optimal feedback strategy at time u1, at time 1, and we have calculated the optimal cost to go at time 1. So now the only thing remaining is to go to v star 0, v0 star. v0 star of x0 is going to be, I will first add the incremental cost at time 0, and it is x0 square plus u0 square. I would of course have to minimize with respect to u0, x0 square plus u0 square plus expected value with respect to w0, and in this case I will substitute there v1 star. v1 star of x1, and x1 is x0 plus u0 plus w0. Okay? So now let us substitute that v1 star description. Let me first check if it was correct or not. Yes, it was correct. And now I can actually make that substitution. So I have minimized with respect to u0, x0 square plus u0 square, plus I will calculate 5/3 times expected value with respect to w0 of x1 square. x1 is this thing. x0 plus u0 plus w0 square plus 2. Expected value of 2 is 2 itself. Okay? So I just have this. Now this is minimized with respect to u0, x0 square plus u0 square, 5/3. Let me take this expected value again, distributing this summation into these two factors, the deterministic factor and the stochastic factor. The deterministic factor is going to be x0 plus u0 square plus 2 times x0 plus u0 times w0. But when I take the expected value of that term, expected value of w0 will be equal to 0, which means that there won't be any cross terms. Plus, I would have expected value of w0 square, which is the variance of w0, which is 1 plus 2. So I would have minimized with respect to u0, x0 square plus u0 square plus 5/3 x0 plus u0 square plus 5/3 plus 2. All right? So now I'm ready to minimize with respect to u0. Here again, I don't have any constraints on u0. That means that taking derivative with respect to u0 and equating the result to 0 would be sufficient for finding the optimal u0. So when this is a quadratic function, okay? So if you don't have any constraints, a quadratic function is minimized at the point where the derivative of it is equal to 0. Okay? But if you have a constraint on the input, suppose that you have a constraint on the input and you are looking at the minimum of this function in this interval. Okay? In that case, you see that equating the derivative to 0 would give you a solution outside these constraints. Okay? If you are looking for a solution in this interval, then when you have a situation like this, when the minimizing point of the quadratic function is outside these constraints, then the minimum is achieved at the boundary. Okay? So here, this equating the result to 0 and solving for u is only valid when you don't have any constraints on the input variable. Okay? When you don't have any constraints and when you have a quadratic function, equating the derivative to 0 and solving for u would give you the optimal solution. But if you have constraints, then you have to check if this minimum point is inside your constraints or not. If the minimum point is not in your feasible region in this interval, then the optimal solution might be at the boundary of your constraint region. Okay? But here we don't have any constraints on the input, so that is why I can take the derivative, equate the result to 0, and solve for the input, and that would be my optimal solution. All right? So in that case, I would have, if I take the derivative with respect to u0, I would have 2u0 plus I would have 2 times 5 over 3 x0 plus u0 is equal to 0. And I can cancel these 2's here. So I would have u0 plus 5 over 3 u0 is equal to minus 5 over 3 x0. So that would give me 8 over 3 u0 is equal to minus 5 over 3 x0. And I can cancel these 3's, which would give me u0 star is equal to minus 5 over 8 times x0. Okay? This is my control, optimal control g0 star at time 0. Okay? Let me check this if it is correct or not. Yes, that is also correct. And now I can substitute this back into my cost function to calculate v0 star x0. So I have v0 star of x0 is equal to x0 square plus u0 star square. It is going to be 25 over 64 x0 square. And I have plus here 5 over 3, and if I subtract this input if I sum this input with x0, it's going to give me 3 over 8 x0, and that is going to be 9 over 64 x0 square, plus I have here 11. Is it? Yes. 11 over 3. Just this constant. So now I can cancel this 3 with this 9. I can write 3 there. So it would be 64 over 64 x0 square plus 25 over 64 x0 square plus 15 over 64 x0 square plus 11 over 3. And that would give me the solution. V0 star x0 is equal to, this is 40, so 104, 64 x0 square plus 11 over 3. And this is going to be, let me try to cancel just divide both sides by 8, so it is 1/3 over 8 x0 square 11 over 3. Okay. So this is the optimal cost at time 0, optimal cost to go at time 0. And now in order to be able to find the optimal overall cost, I need to take the expected value of this thing with respect to x0. Okay? So here, this J star, the optimal cost after all optimal feedbacks, it is expected value of V0 star of x0. So expected value of this thing, it is 13 over 8, expected value of x0 square plus 11 over 3. Again, this is the expected value of the square of a random variable. If the random variable has 0 mean, then this is variance. But if the random variable is not 0 mean, you have to add to this the square of its expected value. So this is going to be 13 over 8, variance of x0 plus expected value x0 square plus 11 over 3. Okay? So both of these quantities are 1. So the sum makes 2. So it is 13 over 4 plus 11 over 3. So it is 39 plus 44 over 12. And this happens to be 83. Sorry, 83? Yes. 83 of 12. Okay? And this turns out to be 6.91. This is the optimal cost. This is the optimal that can be made by applying the Markov policy, by applying the state feedback. All right? So this completes our investigation of these infinite state stochastic dynamical systems and how to calculate the cost function and how to calculate the optimal input feedback strategy. And in the next lecture of this week, we're going to try to generalize these ideas for specifically linear Gaussian stochastic systems. We are going to see that, and actually these examples belong to that case. So these were linear stochastic Gaussian systems. We're going to try to generalize the results on these systems in the case of multidimensional inputs and multidimensional states. These were just scalar examples with scalar inputs, and we're going to see that even if the system has multiple states and even if the system has multiple inputs, for linear Gaussian systems, we're going to see that the optimal costs and the optimal inputs would turn out to be similar to this. Optimal inputs would always turn out to be, in the case of a linear feedback, like this, and the optimal costs would always turn out to be quadratic if we have a quadratic cost function. Okay? So what these are for the next lecture. Thank you very much for watching. Bye.